Okay, so when we're investigating the motor effect is how the magnetic field of a wire interacts with the magnetic field of a permanent magnet. So what I've got here set up, I've taken two clamp stands. I've placed a conducting wire between them. I've then just simply used the points and connected another wire to a power supply, and I've got it connected to power supply. You can see that this side is positive, which means that the current is flowing from the right side going down towards the left side. And if we know our right hand rule, like we've seen in the previous slide, the thumb points in the direction of the current, so therefore my magnetic field is actually moving over the top, underneath the bottom, and back up this way. So we want to see that happen and see that it's actually true. So I'm going to move the magnet out of the way. I'm going to put a voltage across the wire, so we've got a current flowing. So this voltmeter just kicks in with the voltage at some point. I'm just going to make sure it's there. So I've got about 0.5. And then what I'm going to do is I'm going to place my plotting compass, just make sure it's working fine. And then I'm going to bring my plotting compass. So if we bring the plotting compass here, we can see it's pointing in that direction. And then I'm going to take the plotting compass and then bring it to the top. And we notice how it switched direction. So the plotting compass is moving in this direction, which means the magnetic field is going up and around. And then if I bring it to the bottom, but be careful to get the right plotting compass. I think this is okay, I'm supposed to hold it this way, sorry, my apologies. So that's the plotting compass in that direction. Bring the plotting compass to the top of the wire, and you notice it flips. So yes, so thumb pointing in this direction, the magnetic field is moving over the wire, underneath, and then back up this way. So let's put the power back off. And this time let's put a magnetic field. Now notice the magnet that I'm placing is at right angle. So the magnetic field we have from here to here. So it either is, I can actually work that out. So the plotting compass is pointing, if we have a look now, because the magnetic field of the magnet will be much stronger than the wire and there's no current, we can see that the plotting compass is pointing from here to there. So this must be my north, that must be my south. So now let's see what happens. Let's put in a voltage, and I'm going to bring the camera closer now to the wire, and I'm just going to drop the camera a little bit lower so it's parallel, and then I'm going to add a voltage in. And once the voltage kicks in, you'll see that the wire jumps up, and if the wire moved up, that means that there is a motor effect taking place. So if I try and tap that wire, you notice it's pushing upwards. So that's a force. So that's a force exerted on the wire by a magnetic field that is parallel with the conducting wire. So if I bring the camera view back to the top, you'll notice that the wire is parallel with the direction of the magnetic field. That's the only time you're ever going to get motion. So let's test that. Let's take that off. And let's put the magnetic field being parallel with the wire. And let's see if I put the power on, what happens. So we'll notice that the voltmeter will kick in now with a little voltage. And notice there's no real lift on the wire at all. However, if I swap there you go. So you'll notice that as I turn it to be at 90 degrees, notice how the wire lifts. So that is for you to show students that the magnetic field must be at 90 degrees to the current carrying wire in order to create a motor effect. Now let's swap the current around. So you can ask students at this point, how would I swap the current around without actually changing the wire or flipping the wire around? So most students will tell you, okay, yeah, you can do that. But a simple thing to do is change the polarity. So we switch the power pack off, and now we just swap the wires around. We make the other end positive. And we make the other end negative. So now we're reversing the current. So now the current is going to moving from left to right. And then I'm just going to make that wire a bit more, with a little bit more tension, just put it across. Make sure my magnet is there. Switch the power pack on. automatically kick in a voltage, current will flow, and then we'll notice that the wire will actually move down. So this now leads you to discussing with the pupils how we could predict which way the magnet is moving. But one of the other things that we can now discuss is the formulas for the motor effect. So we can talk about F equals current times magnetic flux density times the length of the wire. And we can introduce some equations and calculations with the students. But what we've done here, we've shown that motor means movement, and we clearly have a movement in the wire. Switch the power pack off, we get the wire going back to its original position. Switch it back on. Because the current is reversed, the wire then will move in the opposite direction. Now we can also change the magnet around. So here the wire is moving down, but I can also, instead of changing the current around, I can change the magnetic field around. So from a top view now, I'm going to change the magnet around, and as I do that, you can lift that wire, it's not a problem. And then as I lift it, notice what happens to the wire now. Now we notice that the wire is actually lifted. So now we can discuss with pupils how we can actually change the movement of the wire, either by changing the direction of the current or changing the direction of the magnetic field, as long as the magnetic field and the wire are at 90 degrees with each other. So let's bring it back down by swapping just, and we can see that movement. The wire is following the magnetic field, and there we go. We do that, and there we go. The wire is being pulled down completely.